Hi folks, welcome back to Physics with Captain Rod. I'm making this video here to provide an example of how to draw free body diagrams and use them to predict the behavior of a system. So what we're looking at, imagine we've got this incline here that's inclined at 30 degrees from the horizontal. We've got this 30 kilogram crate or something sitting on it, with somebody applying a 200 Newton horizontal force to that crate. So this is some sort of external force right here applied by a person pushing on it or something to that effect. For this example here, we're going to assume that the frictional forces along the surface are approximately zero. That's why I've got a coefficient of friction approximately zero here. And what we're going to do is try to calculate the acceleration of this object. So it all starts with how to draw the free bodies. And I always recommend, especially in first semester physics, put the gravitational force in first, and after that you're looking for contact points for all other forces. So the 200 Newton force is an applied force that's already shown in the free body. I'm going to go ahead and add the gravitational force. So the gravitational force on this object would be down. And because this object's 30 kilograms, that's going to make that force vector around 300 newtons. So I'm going to go ahead and draw it quite a bit larger than the 200. I'm not going to actually get a ruler out. I'm just going to at least eyeball it. So that's the force mg. And again, that would be approximately 300 newtons because the mass is 30 kilograms and the gravitational acceleration is around 9.8 meter per second. All right, so here's my first force in the free body. Next, you look for surfaces in contact. Now, right here is a surface in contact. That's going to give us a normal force, which is going to be kind of up and left on this object or down and right on the incline. My free body is a free body of this object. So the normal force is going to go in a direction something like this. Oops. Now, hopefully you've seen my videos on free bodies. These force vectors have what's called a line of action. Whether I put the normal here or down here doesn't matter. You can put that normal vector anywhere along this line. For that matter, the mg can go anywhere along this line and so forth. If there were a frictional force to consider, that force would go tangent to this surface, and you'd actually have to do a little pre-calculations to determine the direction of the frictional force, but I'll save that for another video. Since we're looking at a approximately frictionless surface, we're going to forego the frictional force. All right, so my free body is done. That's it. Those are the only relevant forces acting on that object. All right, so now the next step is to write a Newton's second law equation. Now remember, Newton's second law, net force equals mass times acceleration. And remember, this is a vector law. When you're dealing with vectors, the first thing you want to do is decide on a coordinate system to work in. Now I'm going to go ahead and draw, just for the time being here, a standard, what I would call a standard right positive type of coordinate system here. All right, so x, y. And I want to talk about how this coordinate system now relates to this picture. The acceleration vector for this box is either going to be this way or perhaps this way. And I haven't even begun thinking about things numerically yet. So, at this point I don't even know which direction this thing's accelerating. But it's got to be in one of these two directions. It's just not physically possible in this problem for it to accelerate this way or this way. So the acceleration vector has to be parallel to the incline. Any Newton's second law equations that we write in this equation here, because the acceleration is either up and right and down and left, any Newton's second law equations we write are going to have ma terms in both directions because the acceleration is going to have a component in both the x and y directions. So to get around that, what I'm going to do, so I'm going to take our coordinate system, probably don't need it quite that large, and what I'm going to do is rotate it so that it is parallel to the acceleration. So I'm going to go ahead and put a coordinate system right here with up and right positive. Now you could also do down and left positive, that doesn't matter. I'm just going to arbitrarily decide to call up and right positive, and the advantage to doing that is now the acceleration vector is parallel to my x-axis. All right, so now we're going to go ahead and start writing some equations here. If we were dealing with friction, we would need the normal force. So I would normally recommend to start by writing a force equation in the y direction. However, in this problem, there is no friction, so we're not going to need that normal. So what I'm going to do here is concentrate on a force equation in this direction. Now, before I write the equation, I'm going to go ahead now and look at some of the force vectors here that we have to consider. The normal force does not have a component along the x-axis, so we don't need to worry about that. But the gravitational force, mg, does. So the first thing I'm going to do is I am going to draw the vector components for that force. And I'll go ahead and draw those in red. So I'm going to break this force vector into components which are parallel to the coordinates I have chosen to work in. There. So in red here, this is now the y component because it's parallel to the y direction of this force vector. And this one is now the x component of this force vector. Angle-wise, now this is 30 degrees, which makes this angle 60, but this would be a right angle. So that's going to make this angle right here 30 degrees. So by basic trigonometry, because the hypotenuse here is mg, this one, which I would call mgx, it is the x component of the gravitational force, is equal to mg sine 30. And this component, because it's adjacent to the 30 degrees, that one's equal to mg cosine 30. All right, so the gravitational force vector now has been broken into components parallel to the coordinate systems I'm working in. Next, let's talk about this 200 Newton force. It also should be broken into components. It has a component this way, parallel to the x-axis, and a component this way, parallel to the y-axis. There we go. Okay. All right, so 30-degree angle, that's going to make this angle 30 degrees right here because these two lines are parallel. And this component now, looking at this right triangle, this component is opposite the 30-degree angle. So it's going to have a magnitude of 200 newtons times the sine of 30 degrees. This one is adjacent to the 30-degree angle, so this one's going to have a magnitude of 200 newtons times the cosine of 30 degrees. Right. So I've drawn my free body, and here, those are the force vectors in black. I've chosen a coordinate system to work in. I've now broken the force vectors down into components that are parallel to my coordinate system. The normal didn't take any work because the normal is already parallel to the y-axis and it doesn't have an x component. Now, as far as a force equation, the acceleration is either up and right or down and left. I haven't even ran a number yet to consider that, but the force vectors that are relevant are this one and this one. I'm going to go ahead and write a force equation now for what I'm calling the x direction. The sum of all forces in the x direction equals ma. I've got up and right positive, so I'm going to go ahead and call up and right the positive x direction. And that's going to be this force vector, 200 newtons, times the cosine of 30 degrees, and that's positive because this arrowhead points up and right. Now we're going to have this guy, the x component of the mg here, so I'm going to put minus mg sine 30. The minus sign is because this force vector is pointing down and left, and I've got up and right positive. And there are no other x components anywhere in this picture, so equals ma. So here's our Newton's second law equation for this free body applied in the x direction. So what I'm going to do here is I'm going to pause this for a moment, calculate a value, and come back. All right, folks, so I ran that, and what I got is about 0.87 meter per second per second. So again, this is just a numerical value. The mass is 30 kilograms times 9.8 meter per second times sine of 30, and then divide by the 30 kilograms. And what I get is, for the acceleration, I get positive 0.87 meter per second per second. The positive sign is saying that my assumed direction is correct. When I wrote this equation, I assumed up and right positive, and this thing came out positive. When we worked out numerically, it means the assumed direction is correct. So the acceleration of this object should be 0.87 meter per second in this direction. Right? So again, the point of this video was how to draw a free body diagram and use it to predict the behavior of a system. In this case, we predict that the acceleration will be 0.87 meter per second up and right. Hope this video helps. Have a great day.